Greetings, the Astro 30 here yet again, and welcome back to AEL. If you're new to the channel, please go down below and subscribe if you haven't done so already. Anyway, today we're going to be looking at more fun with the 555 IC. In this case, we're going to be looking at a sound activated switch. Now, this is a circuit I found online with a couple of modifications. They were driving the relay directly from pin 3 of the IC, which is not a good idea. These ICs are only good for a current delivery of about 100 mA. Any higher than that and you can run the risk of destroying the IC. So I added an output driver. However, the rest of the circuit is basically the same as the one I found online. Now, this is configured as a monostable flip-flop. So when we provide a pulse to pin 2, the trigger, in this case bringing it to ground, this will set the output to high. With the output high, the transistor turns on, relay turns on. Now, whilst it's in the high state, well, pin 7 is no longer at ground potential because that's the discharge pin. So the capacitor is allowed to charge here, this 100 microfarad, through this 100k resistor. Now, the time constant between these two values gives us around about 11 seconds, because once the capacitor has charged to 2/3 of the supply voltage, in this case 12 volts, then pin 6 is activated, then this output state then goes low. When the output state goes low, the relay drops out, and well, we just wait for another trigger input to put it back into a high state. Pin 2 is tied high with this 1k resistor, and this transistor here at the input is basically just a switch. So when an input signal comes through here to the base and is of a sufficient value in the positive direction to turn this transistor on, well, ground is brought up to pin 2, which then triggers it to the high state. This capacitor here and this resistor just form a low pass filter, and we have a DC blocking capacitor here. And that's pretty much the basic operation of this simple circuit. Now, how well the circuit works remains to be seen. I don't know how sensitive this input stage is going to be, or if it's going to work at all. So these are the things I've got to find out. So the first thing I'm going to do is I'm going to build up this end of the circuit without the transistor connected, but with the... That was a fail. Let's try that again. I'm going to build this 555 circuit part up first and test it, just to see how it operates. And if the timing constant is 11 seconds, thereabouts. There is a calculator online you can use to calculate that. Supply voltage is kind of irrelevant. And just for the trigger pulse at pin 2, I'll just simply bring it to ground to trigger this circuit high. So let's get building. So there's the 555 circuit built up on the breadboard there. It is messy as anything. That's the driver transistor, the back EMF diode or snubber diode, and these leads going off are going to a relay sitting just off screen here, that particular relay. I've got one channel of my power supply set to roughly 12 volts, 12.3 in this case. So without any further ado, I'll turn the load on. Well, that's kind of unfortunate. The output state is high. I've got an LED connected in series with the base of this transistor, just to give me an indication of when it's in the high state. There's also another LED here, a red one, which indicates when it's in the low state. That just goes, the cathode goes to pin 3, through a resistor to ground. And there is a slight little bit of a pulse here. I'm actually getting the sneaking suspicion that pin 2 needs to be tied high. So I'll put that 1k resistor in on pin 2 in the positive rail and see if that makes a difference to its output state. So I can probably do this with it turned on. So pin 2 and positive, which is pin 4. Well, not much happened. Oh, there we go. So now it's in the low state. So the capacitor is charged sufficiently enough to trigger pin 6 to flip it into the low state. So now I've got this wire which goes to ground. I'll just touch it to a ground when I can find one. There we go. 4, 5, 6, 7, 8, 9, 10. Close enough. Let's try that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Very good. Okay, so that's working. So next it's to build this input transistor stage and connect it to pin 2 and see if by pumping in an audio signal at the input here, well, it trips the relay to turn on. Alright, that transistor stage is built. I've got my oscillator from the oscilloscope going through my attenuator, which I'll make sure it's turned all the way down, off of the output of the oscilloscope's generator, and I'm set to roughly 100 Hertz because I'm not really sure of what the frequency response of this low pass filter is, where it starts to roll off. So I'll set it at 100 Hertz. It'll probably work at kilohertz, but anyway, I'll turn the circuit on. We're in standby mode is what I'm going to call that. So I'll just rotate the pot, and I'm going significantly high, and I'm at max, and there's no change to the state of the circuit. Well, that was unexpected. So what's going on with the circuit? Well, I don't actually know. So it might be a good idea if I start probing around with the oscilloscope just to see what sort of signal we've got coming in after the capacitor, after this resistor to the base, etc. And just, have a probe around. Alright, oscilloscope's connected to after the capacitor, before the base of the transistor, so on this 2K2 resistor. And yes, there is a signal there. It's about 2.38 volt peak to peak, which is not as strong as what the output is originally from the oscillator. I can compare it to what its input is, 2.58. So we've got a little bit of a loss there, but not a great deal of a loss. So yeah, okay, so that's going after the capacitor, so there is a signal there. How about when we connect it to the base of the transistor? Oh, I just lost the resistor. Let's try that again. Alright, at the base of the transistor, it's a little bit less again. So, should be enough to turn the transistor on, I would have thought. Alright, let's measure what's going on at the collector, which is pin 2 of the IC, which just triggered the circuit, by the way, as soon as I connected the probe to it. But there's no signal there, nothing. We should be seeing, some form of negative dip, but we're not. So let's just try something. Let's eliminate this capacitor altogether. Whoa, okay. There we go. Yeah, that kind of looks square wave, but that's alright. That's what I mean about that negative dip. That's what we should be seeing. And the relay just dropped out. And the relay just engaged. Let me change the frequency of the generator, because the time base of this to get it to display properly is a pain in the rear. Okay. That's a little bit faster of an update. Alright. According to what's at the collector, we've got 9.75 volt peak to peak. And it's causing the circuit to stay in the active state. However, that seems to me to be a little bit on the non-sensitive side. So that means that this input circuit is not really the best, and I mean it works with it bypassing the capacitor, which is not what we want. So either this 1K resistor is too low and needs to be increased, or it's maybe an impedance issue here at the input. I don't think it's an impedance issue. I think it's more like it's this resistor is too low of a value. What I will do is, though, just out of curiosity, is I'll add a resistor from this side of the capacitor, the transistor side, to ground, say 10K, just to give it some form of input impedance here across this capacitor, and see if that makes a difference. I don't think it will. Alright, I've got a 22K here to ground. I couldn't find an open packet of 10K resistors. I didn't want to open another packet just yet. I mean, they're only 88 cents, but who cares? Now, I don't think it's going to make any difference, but I'll rotate the pot. Oh, actually, now we can see a negative, which we weren't seeing before. So yeah, it does need that resistor, but it's still reacting too slow. And what I mean is that this is just not sensitive enough. So I reckon that this resistor may be too low of a value. So let me up that to 22K also and see if that makes a difference. Alright, the 22K resistor is now in place of the 1K. So I'll rotate the pot. Yeah, it is more reactive. I'm turning it up less now. Yeah, it's still not reactive enough. I'm going to have to play with some resistor values here and see if I can make this circuit operate a little bit better. Alrighty then, I've done some playing around off camera with some resistor values and stuff, and I've come up with a solution that makes this circuit more viable and functional. I've basically turned this first transistor into a Class A amplifier. That is, the 1K resistor that went between pin 2 and the positive rail, or the collector resistor of this transistor, is now a 100K. I have, from the collector to the base of this transistor, a 1 megaohm resistor as negative feedback. And the input resistor that goes between the capacitor and ground here is also 100K. And now it takes very little input signal to trip the circuit. So I'll turn the circuit on, we're in standby, and if I slowly rotate the pot, bam. And we're only probably at the 8 o'clock position on that particular pot on the attenuator. And if we look at the oscilloscope screen, we can see that it's a reasonably nice sine wave there. And if I increase the volume even further, well, it's acting as an amplifier, but eventually we're going to hit clipping. But that's fine, because all we need is for pin 2 to be brought to ground potential. So that makes the circuit more viable because the input sensitivity of this is pretty low, which is what we want, because we don't want to be detecting a sound signal at 2 or 3 volts peak to peak before it actually does anything. So for example, what would you use this circuit for? Well, you could connect an electret microphone to the input capacitor with a resistor going to the positive rail on the positive point of the microphone, and as soon as it picks up sound, it will turn the relay on. You could also use it in an audio circuit such as a subwoofer to detect whether an input signal is present, and then, you know, turn the relay on. Those were my proposed uses, but let me just change the generator. Not that. Idiot. Let's try that again. Turn that to 100 Hertz. See if the circuit still operates, which, yeah, its frequency response to that transistor is a little lower on the 100 Hertz mark, but just give it a little bit more wick and yeah, it'll still react. So that's perfectly fine. I'm going to stick that back to a kilohertz because the refresh rate of the oscilloscope is too slow on frequencies below 500 Hertz. So we go back to a kilohertz. I mean, it's not a perfectly clean sine wave, but it doesn't have to be. We're not actually interested in the amplified signal after the transistor to do anything except trigger the 555 IC. So what the actual input voltage is going into the circuit, I'm going to find out by measuring it. Well, according to the oscilloscope, it's about 130 millivolts peak to peak, or 42 millivolts RMS, which should be sensitive enough for an electret microphone, which is going to be my next little bit of an experiment. And this is what it's all about, is experimentation. So I've got a microphone insert here, an electret microphone, you know, standard one. That's connected to the circuit from the ground and the hot lead going into the capacitor. Got a 22K resistor going from that same connection, which is the positive of the electret microphone, going to the positive of the circuit to give the microphone a bias voltage, otherwise the microphone won't work. So I'm going to be very quiet and turn the circuit on. How about that? All I did was tap the microphone and it worked. That makes this circuit pretty sensitive, although I'm talking and not much is happening, so hello, hello. Okay, I have to be pretty close to the microphone for it to pick me up. And just for reference, that's what's going on the oscilloscope. I mean, yeah, it's probably not as sensitive as I want it to be. However, that can be experimented with a little bit further as well. Hello, hello, hello. I'm talking pretty loud and it's still not triggering the circuit. Hello, hello, hello. Yeah, I still have to be pretty close to the mic for it to pick it up. So that means that my input sensitivity is probably not high enough. Let's see what happens when I remove the 100K resistor going to ground. And it tripped. Yeah, no, it needs that resistor in there. Okay. So put that back in. Maybe I need to decrease the feedback resistor. So I'll put a 470 in there instead and see what the difference is. Well, anyway, messing with the resistor values further, like the resistor here for the microphone, lowering it made no difference. Increasing and lowering that 100K resistor there makes it too sensitive that it just makes it permanently on. However, if I was to talk a little bit louder or closer to the microphone, hello, hello, it will eventually click on. So for picking up sensitive sounds, it's not really practical. But for the purposes of, like, you know, using it to detect a line signal or audio signal coming into an amplifier, works fine. Or if you just wanted a voice operated switch where you just start talking into the microphone and, well, you know, it clicks on and off. So if I was just to talk normally into the microphone, which I'm doing, and I'm about 5 centimeters away from my mouth, and I'm talking at a reasonably normal level, it's still sensitive enough for the circuit to pick up, although if I pause too long, this capacitor charges quick enough for it to reset the circuit. So yeah, see what I mean? So there's no real way to overcome that issue unless you add an extra transistor to keep this capacitor discharged whilst it's receiving a signal. But I don't find that very practical. But yeah, using this as like, you know, a voice operated microphone is fine. Yeah, but the practicality of this circuit is probably not that practical. But it works for what it is. Now, having said that, you can mess with the 100k and the 100 microfarad capacitor to give you a longer on duration. So, for instance, if you increase both of these values, well, it will stay on a lot longer. I've figured with 1 megaohm and 1000 microfarad, the circuit will stay active for roughly about 4.5 minutes, which is quite a considerable long time. Conversely, if you lower these values, well, the on time will be shorter. However, I think 11 seconds is reasonable for this particular application to keep the relay on long enough to do something. But all this was basically an experiment with the 555 and making a sound detection switch, which, yeah, it's not the best. There are other options you could do. You could use a op amp here at the input instead and give it much more gain and just reconfigure the 555 timer to work happily with it. And yeah, you'd end up with a pretty good working circuit. However, I'm going to leave this particular circuit here in this video because I've proved the point. The circuit works to a point, but it had to be modified. So to conclude this video, let's have a look at the changes on my schematic. And there it is there. It's not that much different from the beginning. And that leaf blower is annoying in the background. So here I've changed this to 100k. That is supposed to be physically joined. There's now a 1 megaohm resistor going between the collector and the base. And there's a 100k resistor here going to ground after the input capacitor. And if you were to use a microphone that I've got here, well, the positive connects there, the negative of the microphone connects to ground, and you add a 10 to 22k resistor between the input pin here and the positive rail, and that will give you a sound operated switch using an electric microphone. So I hope you found this video interesting. If you did, please remember to go down below, subscribe, like and comment if you haven't done so already. And yes, this circuit can be modified even further to work even better. But this was just an experiment. It's not a final circuit. I may make a PCB for this because it does work fine with a signal being injected into it from an oscillator. So around about, you know, the 100 odd millivolt mark, 200 millivolt mark, whatever it was, which is fine for, you know, switching an audio device on and off when it detects a signal. So yeah, I'm going to leave this video here. Thank you for watching. How cool is that? Clap activated switch.